For this lesson, what we're going to be talking about is we're going to be talking about friction. Now, friction is known as a reactionary force. And what it does is that it opposes the motion of an object. Friction depends on two things. It depends on the type of surface in contact and the amount of the normal force as exerted by one object on the other. And a way to picture that is I want you to think about trying to pull something hard or push something heavy along the ground. The odds are if you're trying to push or pull something, you're going to want to often try to have your force applied this way. You'll find it's easier, like if you're trying to drag a table, if you're lifting it on a slight angle. Why is that? Because when you're doing that, well, some of your force will be going this way, of course, but then there will also be a force applied in the vertical. If this is happening, what's going to happen to your force normal? Well, by definition, it's going to decrease. Less normal force means less friction. Anyways, when we're looking at what our formula is, we're trying to figure it out. We have the symbol of mu. Now, the formula for is mu is equal to force friction divided by force normal. Now, mu is known as the coefficient of friction. Okay? Now what it is because what we're doing is we're dividing force friction by force normal, what we have is that mu ends up becoming a ratio value. And because it's newtons divided by newtons, it therefore has no units. Now there's two general types of friction when we talk about it. If the object is moving, what we're referring to is known as kinetic friction. On the other hand, if we're talking about an object at rest, it's known as static friction. And the way we symbolize those is we're going to use this as mu, so it's like a little u k, and mu s. So for calculation purposes, in this course we're always going to be finding our kinetic friction. Now listed below here are some tables so we can compare what static frictions are to kinetic friction values. And what you're going to notice, I don't expect you to memorize these, all I would expect you to know is that in most cases here, the static friction is going to end up being higher than the kinetic friction. Now, you know this instinctively. If you've ever tried to push something that's really heavy or pull something that's really heavy, you'll know the hardest part about pulling it is always those first few seconds. Once you get something moving, it becomes much, much easier. So when we talk about static friction, the maximum static friction value is always going to be Fs is equal to mu times force normal. Now that's what it'll be as its maximum. The minimum static friction may be anything from 0 to maximum value depending on the situation. So what we've got here is we've got an illustration. So you can picture the graph here compared to movement. So when you look down at the lower part of the graph, we can see that here in general this line represents the kinetic friction value. And this is where we have our maximum static friction value. So what's happening here is if you've got your object, you're starting to pull it. And as you pull it, the tension force is going to be larger than the static friction, but you're still going to be fighting it. And as it gets faster and faster, and you have it sliding at a constant speed, that is the point in which the kinetic friction is what's affecting the movement. So let's go through one example and how we apply this to what we've already learned. Phyllis, whose mass is 58 kilograms, is sitting on a 2 kilogram sled on a flat, level, snowy field. Calculate the magnitude of horizontal force Frank must apply to Phyllis so that she accelerates from rest to 2.6 meters per second in 4.2 seconds, given that the kinetic friction between the snow and the sled is 0.16. So the first thing we're going to do in this question, just like we do with every question, is we're going to draw ourselves a free body diagram. So there's my free body diagram, and we know Phyllis's mass is 58. Now yet again, there are four forces affecting Phyllis. We've got our force gravity. She's on a surface, so therefore we have our force normal. We've got our force applied, because they're trying to get her to go faster, so they're accelerating. And of course, we know there's going to be force friction. Now from there, what we need to do is we need to put things into a T-chart. We're dividing into the vertical and the horizontal. So we'll start with the vertical in this case. we've got our force gravity. Now force gravity is going to be equal to mass times acceleration. If our mass is 58 and we know acceleration due to gravity is 9.8, we therefore know that the force on Phyllis for force gravity is going to be 568.4 newtons. And it's important that we write that this is in the down direction. Now we don't know the force normal, but we know the net force is going to be 0. Now since Phyllis is neither accelerating up or down, we can therefore conclude that the force normal has to be in this case the same value as force gravity, except in the opposite direction, so 568.4 newtons up. Now in the horizontal, we've got two forces. We know we've got a force applied, and we've got a force friction. Now we know the force friction is equal to mu force normal. The mu in this case is going to be 0.16, and we just figured out that our force normal is going to be 568.4, which makes the answer to this question 91 newtons. Now since we have the applied force going to the right, therefore force friction has to be going to the left. Now in this case, we know that the net force is going to be equal to your force applied plus your force friction. Thing is, we don't know what our force applied is. What do we know? We do know that Phyllis starts at rest, so V1 is going to be equal to 0. We know that she eventually speeds up to 2.6 meters per second to the right. We know the time is 4.2 seconds. So from there, with our kinematics we learned in the previous unit, we can figure out our acceleration. So A is equal to change in V over T. So if we plug that in, we see that the acceleration is equal to 0.62 meters per second squared to the right. Now if we know the acceleration, then if we plug it into F net is equal to ma, we can therefore figure out that since she's 58 kilograms and 0.62, that her force has to be 35.9 to the right. Now this is a little bit messy, so if you give me a moment, I'm going to erase some of this to make it easier to read. So now that we've erased and we have a little bit of extra room, we now can establish that the net force on Phyllis is going to be 35.9 newtons. So if we know, and I will continue to write this up here, that this is going to be 35.9, and we're trying to figure out the force applied, now I can't simply just add 91 newtons. Why is that? Because the net force is to the right and the friction is to the left. So therefore I'm going to subtract this value. So therefore I can figure out that my force applied is going to be equal to 126.9 newtons to the right.